Didn't get it on camera, thought I had. But anyhow, if I accelerate a mass m from rest using a net force F net, what's going to be its velocity at position x? Now, what we're doing is we're going to define work and kinetic energy. Okay. So can we set that up with symbols and give a quick answer? All you need is some equations of uniformly accelerated motion. I'll even give you a hint. You're probably going to want to use the fourth one. Be very familiar with equations of motion from having done problems. And you should probably pretty quickly see this one, especially since you know that V naught is 0. You get V is the square root of 2a times x minus x naught. Now, A isn't given, but we got net force and we got mass. It's 2 times F net over M times X. X naught is also 0, since we said that X naught was 0. Okay. Well, that's what we get, but I'm going to go back to what V squared is. V squared is this product. F net x equals 1/2 mv squared. Okay. Now, in general, I'm going to write this as an F net times delta x, because of course x naught's not always 0. We might have an x minus x naught here instead of an x, so we'd have a delta x here. So this simplified version of that, I might have left x naught in there, but didn't want to confuse the issue. Find that V is 0 when x equals x naught. What if V isn't 0? Well, let's think of that just to get a little terminology. Net force times delta x is work. One half mv squared is kinetic energy. Okay. Now work, I'll generally abbreviate with a capital W. Okay. A lot of times notations are lowercase w. I'll probably write a capital W. Kinetic energy, I like to write it as KE, but more standard notation is just K. But to distinguish this from like a force constant or something like that, I'll usually write KE. It's a little less ambiguous, but your book is probably going to write K. All right. Now, We start with V naught not equal to 0. Well, we're going to use delta x for x minus x naught. So I can write v squared as v naught squared plus 2f net over m delta x. That solve this for f net delta x, and I get one half mvf squared minus one half mv naught squared. So the work equals final kinetic energy minus initial kinetic energy. The other thing is, this is the work done by the net force. So I want to be very careful to write net as a subscript on work. Okay. If I push a box across the floor, the work done by the net force is changing its kinetic energy. So if I speed the box up, I'm increasing its kinetic energy. Okay. The work I do is not the work that increases its kinetic energy. I do more work than the change in kinetic energy because friction requires me to push harder than the net force. Force I exert has to be greater than the net force because the friction opposes me. Okay. We don't want to confuse the work I do with the work done by the net force. That's very important. Okay, well, what's this good for? Well, you're going to see pretty quickly that's really good for a whole lot of stuff. Okay, it can allow us to bypass the equations of motion and simplify a lot of problems. Okay, so there we have that. Okay, so let's see. I'm just debating because, as I mentioned at the beginning of class, the chapter appears to cover just work and kinetic energy. Okay, but the homework for the chapter, which is correlated with the same edition that I'm looking at with the text, I think, double check that, appears to talk about potential energy, which isn't mentioned in chapter 6. Chapter 7 gets into potential energy. Chapter 6 is a relatively short chapter on work and kinetic energy. Well, let's just do an example of them that I've got a string over this pulley. It'd be fairly easy to mock up. You can get a chance. I've got a string over that pulley and attached to this cart. And on the other side of the string, I've got a suspended weight. Let's say I've got a 20-gram weight. Okay, 20-gram mass. 0.2 of a Newton weight. Okay, what's going to happen? Well, it's going to accelerate this thing. We'll do that in lab. It's going to accelerate along the incline and reach some maximum velocity. If we assume that the net force on that system is just a force of gravity on the 20-gram weight, we can analyze this using the work energy theorem. So we have this. This is level. And friction, we assume is negligible. It's pretty low friction. Okay, you got well less than a 1% coefficient of friction, 0.01 coefficient of friction there. Probably about 0.003 or something like that. Okay, 500 grams, et cetera, et cetera. Question is, if the system accelerates through, say, 80 centimeters, how much does its kinetic energy change? Well, we've just written down the relationship. I'll write it down for you again. It's on the other board. Okay. If you multiply the net force by the change in position, you get the work, which is equal to the change in kinetic energy. And thank you, camera, for zooming back when nobody asked you to do it. Thing doesn't have a continuous zoom, but we looked up, we got a pretty good zoom on that. Okay. Okay. So what do you think? Let's just talk about it for a minute. Okay, now just to put a few arrows here, we have all this M2G, where M2 is implicitly 20 grams, right? So we'll just be explicit about that. M2 is 20 grams. Okay. Then you're going to have M1G downward, right? And this is M1. Then we're going to have a normal force upwards. And since there are no other forces acting in the vertical direction, these have to be equal and opposite due to the fact that this is a level track and it's strong enough to support the car. Okay. So we're not accelerating upward or downward from the track. Okay. Another force we have is there's a tension in the string. Okay. And there's a tension in the string over here. It has the same magnitude, assuming it's a light string. Okay. So what's all that come down to? Well, if you consider the cart and the mass as a system, Let's say the only forces in the system are M2G F nominator M1G. I'm not going to use I and J vectors and stuff on this because, well, I'll get back to that in a minute. Okay, your net force is M2G. It's the only force acting on the two mass system. The only unbalanced force. All the other forces, namely the force of gravity here and the normal force here, cancel each other out. Okay, now if we have friction, then we do have another force, and we do actually have some friction. We're saying it's negligible. Okay. If we have a cart with wheels that typically run around 2% friction, then we'd have to have a frictional force here. And we understand that would reduce the net force because this force is tending to make the system go in this direction, and that force would tend to make it go in this direction. Now, what direction does the system move in? It doesn't move in the I direction, the X direction, if you let the X axis go here, because part of it moves in the X direction, but this part doesn't. Okay, this part moves in the Y direction. And these two parts move in mutually perpendicular directions. So we can't put a single direction on this thing, except by the right-hand rule. This system tends to be rotational. Okay, it's a rotational system. We use the right-hand rule, and we find that our thumb goes into the board. Well, for now, we're just going to say we're not going to worry about the right-hand rule and stuff. But I want you to understand that because pretty soon we're going to be talking about rotational systems. And we even started the course with a rotational system, right? So you got some familiarity. But right now, we're just going to say this system tends to accelerate in the counterclockwise, in the clockwise direction. So, okay, it tends to go like this. And that's like the direction of a clock. It's not as circular as a clock because part of it. But you understand that the pulley is going to be rotating in the clockwise direction. So the direction is clockwise. Okay, so what's acceleration? Well, we can calculate the acceleration. And we can figure out how fast the system's going. If it starts from rest, how fast it's going after 80 centimeters. We can figure out how fast it's going after going 80 centimeters. If it starts out at 40 centimeters per second, we can calculate that. We got that fourth equation of motion. It allows us to pretty easily calculate the final velocity given any initial velocity. We don't want to have to bother to do that because actually, in a sense, we get the same answer no matter what we do. And this answer is kinetic energy always changes by the same amount because kinetic energy depends only on the net force and how far we go. Okay, so F net is M2G in the clockwise direction. And what about delta X? This is where delta S is a better symbol than delta X. Because delta X implies motion along a single axis. Okay? And yeah, this thing's moving along a single axis, so we kind of use that. But the whole system, we want to think of the motion of the whole system so we don't get confused and think the tension is equal to M2G. And we'll find out that it isn't. So I'm going to change my delta X after the fact to delta S. More general, doesn't specify X direction, Y direction, what. Okay. And it would apply to systems going on a roller coaster or whatever, where X might not be a natural choice because it implies motion along a straight axis. Okay, so there's another caveat here. It's not really a product of two scalar numbers, nor is this. When we're just worrying about motion on the x-axis, it was okay to write it the way we did. But F net and delta S are actually vectors. And to calculate the work, we do the dot product. So our change in kinetic energy is net force vector dotted with delta S. The direction of F net is in the clockwise direction. What's the direction of delta S? Our delta S. Well, the system also moves in the clockwise direction. Okay. The dot product is just the product of the magnitudes because the angle between a clockwise force and a clockwise motion is zero. And the dot product is magnitude of this, magnitude of that, cosine theta. If the angle between the motions is zero, the cosine is one, and you just get the product of the scalars. Okay. So in this case, the vectors aren't directly relevant, but you do have to be aware of them. For example, if this thing was given a velocity in this direction, then the direction would be counterclockwise. The system would be moving this way, opposite to the direction of a clock, and your F net dot and your delta, your F net would still be clockwise, whereas your motion would be counterclockwise. That's like a 180-degree difference. Cosine of 180 degrees is -1, so you'd have a negative. That makes sense? At least visually? Okay. So you gotta take all that stuff into account. But right now, it comes down to F net delta S. Okay, so let's just forget about all the technicalities that you're going to have to remember about them. You understand that there are technicalities. Let's just come back to this simple situation. This thing is moving in this direction. Okay. Although it doesn't have to be. The whole thing applies just as well if it's initially moving in this direction. Okay. Okay. Well, F net is F net is your M2G. And Run out of room there, so I'll write 0.8 meters. It's shorter than 80 centimeters. Okay, but we'll go with, for the moment, mixed units. Okay, except, okay, M2 is 0.02 kilograms. I'll use 9.8 meters per second squared, but I'm going to round it off as if I'm using 10. What's this equal? Well, 9.8 times 0.8 is about 8. 0.01 times 8 is 0.08, so this is like 0.16 kilogram meter squared per second squared. That's a change in kinetic energy. If the initial velocity is 0, then what is the velocity? Might be out from these boards, yeah. Okay, so look at kinetic energy. Well, kinetic energy is defined as what? Okay, well, kinetic energy, we define that back here. Okay, as 1/2 mv squared. Now it's implicit here, the change in kinetic energy is the change in 1/2 mv squared. Because you have 1/2 mv squared for the final velocity, 1/2 mv squared for the initial velocity. We've got a question. Okay, again, we know kinetic energy is 1/2 mv naught squared. 1/2 mv squared. Okay. Well, they're handy to just be able to solve that for V, because a lot of times you'll do that. You'll know kinetic energy from some analysis that didn't involve the equations of motion. Then you'll be able to find the kinetic energy. Now you want to find the velocity. If you know the mass, you find the velocity. We'll solve that equation for velocity, see what you get. Okay, so this is very easily solved. We get V equals the square root of twice the kinetic energy divided by the mass. Okay. Now this is, if we start from rest, the kinetic energy is this, okay? We start from a different velocity, we're going to get a different kinetic energy. Okay? And the velocity that we end up with is still going to be this. It's just that we're going to be doing this with a different number. Now from rest, okay, what mass are we going to use? Okay, now, it's real easy when you're doing this and trying to find the mass to just focus on 500 grams, or even to just focus on the 20 grams, but all that mass is being accelerated by the force on the 20-gram mass. Obviously, the 20-gram mass is not accelerating at 9.8 meters per second squared, nor is the 500 gram mass. Okay, there are all kinds of confusions that can come in here. So the big caution is take the entire mass of the system into consideration. And this is going to be 520 grams. Since I've got kilograms and meters and everything, I'm going to say that's 0.520 kilograms. Okay. And that's going to be approximately square root of 0.6 kilogram meters squared per second squared over kilograms. More like 0.62 if you want to be technical about it. And that's approximately equal to 0.8 meters per second. Now, assuming I've done all that right, because I have some approximations in there, that's fine. Okay, now what would be what would be the final velocity starting off from 0.6 meters per second? So what's the final velocity starting from 0.6 meters per second? What do we know? We want to find the initial kinetic energy, which we could symbolize as 1/2 mv naught squared. That's going to be 1/2 times 0.520 kilograms times 0.6 meters per second quantity squared. You know, this is about a half, this is about a half, this is 0.36. So we're going to get something pretty close to 0.09. Kilogram meter squared per second squared. It's a little more than that because of that 520. It's 4% more than that. Okay, so it's like 0.0936. All right. That's what I think it is. Yeah, but we're just going to go with 0.09. Keep the numbers simple. We're just trying to really trace the logic and the reasoning that we used in order to do this. Okay. So we'll just write down here. Okay, the kinetic energy is 1/2 mvf squared minus 1/2 mv naught squared, right? We know the change in kinetic energy, and we've just calculated the 1/2 mv naught squared. So we're going to be able to get 1/2 mvf squared, right? So we just solve for that, or Alternatively, just solve for VF because we know M as well. So I've kind of put little circles around all the stuff that we know. The only thing we don't know at this point is VF. It's 2 times this square root divided by M. And it's wrong. Try to do too much in my head. Did something kind of stupid there. Okay. Of course, we could have taken this and solved it for VF to start with. And we wouldn't have had to go through the calculation of the initial kinetic energy, but I want us to see how the initial kinetic energy relates to the final kinetic energy. How the initial kinetic energy, the final kinetic energy, and the change in kinetic energy relate to each other. Having done that, we get the square root of 2, and that's plus, not minus. Then we get all this, okay? This adds up to 0.25, that gives us 0.5. We divide 0.5 by 0.02, we get 100. So we're gonna get like 10 meters per second, so I did something wrong. Oh, M is, look what I did, I put that 0.02 kilograms down here. I was really kind of ignorant after what I said earlier, okay? So we have, that reconciles it. So now we get pretty close to a meter per second. Because these add up to 0.25, double that, we get 0.5, we're dividing by 0.5, get about 99 meters per second. 99 centimeters per second, 0.99 meters per second. Okay. So by starting at 60 centimeters per second, 0.6 meters per second, our final velocity went from 0.8 meters per second to 0.99 meters per second. We only added about 0.2 meters per second, even though we started with an extra 0.6 meters per second. We added 20 centimeters per second to the final velocity by adding 60 centimeters per second to the initial velocity. Does that seem right? Well, it doesn't seem right if you think everything's linear, but we got all these squares and square roots running around, right? Okay. And the kinetic energy is not proportional to velocity, it's proportional to velocity squared. Okay. So the squared velocity increased by as much as the initial velocity. If you square this and square this, the difference is 0.36, approximately 0.36 meters squared per second squared. Okay, the squared velocities changed by the same amount as the squared velocity we added at the beginning, 0.6. 0.6 squared is the same as this squared minus this squared. It's almost like a Pythagorean theorem thing. Okay. Well, there's a lot about kinetic energy and the work energy theorem and the way it's used in this problem. I want to go to a slightly different situation where we start this guy from left and let him accelerate down the incline. Now we know that what accelerates this part is the component of its weight or the component of gravitational force on it parallel to the incline. We should be really familiar with that because we've got a test coming up, right? Anybody already taken it? Everybody get the sample test? Okay. If you're prepared enough that you can do the sample test without having researched the sample test, prepared for the test, all of the problems will differ. It won't be just different versions of the same problem, it'll be different versions of analogous situations. Okay. And the test is kind of heavy towards stuff you've experienced in lab because so many people aren't doing the homework. Okay. But it still applies the same principles. So you should be familiar with the situations. For future tests, will be a little less generous on that. But the problems are not trivial problems. They're challenging problems for the most part. So I'm comfortable with it. Trying to give everybody a chance to get off to a good start here. All right. Well, if the cart could have found the incline, and there's no, we could put a weight over the incline, but we're not going to do that. If I set a cart on a level incline, it's not going to accelerate unless there's some other force acting on it other than gravity. Okay. If I pick it up and move it or push it very slowly to another position in the incline, I'm not going to have to do very much work to do that and leave it alone. It's still going to sit there. Okay. Now, if I pick the cart up from here and set it up at the top of an incline, then all I have to do is release it. And there it goes. Okay. That's because gravity is what we call a conservative force. Okay. Conservative means that it acts the same in one direction as it does in another. The actual general definition is that it's path independent. Okay. If I toss this chalk up in the air, it comes back down. Okay. Blue chalk, I got the blue shirt, I'm not even sure that was visible, but you understand, if I toss a ball up, it comes back down, right? Okay. Gravity does work on it as it goes up. It's the product of the force times the displacement. It's a dot product. The force is this way, the displacement is this way. Sorry, force is this way, displacement is this way, right? So our displacement is, if we take up as positive, our displacement is in the positive direction. Force is in the negative direction. They're at a 180-degree angle with each other. They're opposite angles. So their dot product is going to be negative. But the angle is 180 degrees, so the cosine is -1. So it's just you multiply the magnitude of the force by the magnitude of the displacement, and you get a negative amount of work. What does a negative amount of work do to your kinetic energy? Well, change in kinetic energy is equal to the work done by the net force, right? Negative amount of work done by a net force is going to lower the kinetic energy. Now, when you toss something up, what happens? Eventually it comes to rest. Okay? So the work energy theorem tells you that has to happen. Now, what happens? Comes back down. Okay? How fast is it going to be going when it comes back to your hand? Just as fast as it was when it left your hand, if you ignore air resistance. Okay? So if it's a steel ball, very little effect of air resistance. Okay, it's small and it's really dense, so that little bit of air resistance force doesn't do much to its motion. You had a question. Just had an excellent question that I'll answer in the process, okay? Point is, going up and coming down, you had exactly the same force. Okay? It didn't matter which direction you were going, the force was identical. That's what a conservative force is. Now, the question said, well, we've got air resistance, as I was just talking about. When air resistance have the same effect going up as it does coming down? If you're going up, what's the direction of air resistance? If you're coming down, what's the direction of air resistance? It's different. Okay. And basically, air resistance sucks energy out of the thing no matter what direction you're going. Okay. It's not path independent. The work air resistance does going up and coming down, don't want to get into too much technicality. Just it's a different force going up as it is coming down. Okay. The force is not path independent. It changes when you change direction. And friction's the same. You accelerate that cart up the incline, that little bit of friction will eventually enhance the effect of gravity and bring it to stop a little sooner than it would if there's no friction at all. But the friction as you go up is in the downward direction, and the friction in the downward direction is in the upward direction. So it takes a little longer to come back down because you got less acceleration. Gets up a little faster, comes down a little slower. Something we try to measure in lab. Very difficult to measure because it's very difficult to determine the exact instant at which something comes to rest. Okay. So that's a trick I've never been able to trick a system into giving me good results on that. So something we might talk about Friday. Okay, well, anyhow, how it accelerates down the incline. Then your net force is mg sine theta down the incline, independent that's independent whether the cart moves up or down the incline. Now, I was first talk about releasing the cart from up here, but I could easily have the ramp slope like this and give it a push. It'll go up a ways, turn around, come down. If I don't push it too hard, it goes off the end, right? So As it's going up, gravity still exerts a force down the incline, which is why the thing comes to rest. And then after coming to rest, it accelerates down the incline. The force of gravity is still in the same direction. Okay, so it's a path independent force. U is often used for potential energy. So if I lift a concrete block, okay, does gravity do positive or negative energy on it? Use this for positive, this for negative, use this for, I don't know. Okay, want to see thumbs. If you don't know, I see positive, I think I maybe see a negative, and I see okay, well, we got 3 negatives and 1 positive. Okay, well, let's figure it out. What's the direction of the force of gravity? What's the direction in which I just lifted the, yeah, it's up. Okay, if you multiply an up displacement by a down force, you get a positive or negative amount of work. It's negative. Okay. When the force and displacement are in opposite directions, the work done by that force is negative. If you're pushing in the same direction you're moving, the work you do is positive, and that speeds things up. If they're opposite, that slows things down. Okay, so that's not too hard to get into your head. You get that idea into your head, it makes it easier to think about this stuff. So now, would I say that the potential energy of this thing is greater here or here? Well, potential energy is what you get back when you release it. Okay, so if I start here and lift it to here and then release it, when it comes back to here, and with my tennis elbow, I sure don't want my hands to be there when it comes back down, but okay, when it comes back down here, all that energy, all the work that I put into it comes back to me in the form of kinetic energy. We then take this potential energy, convert it to kinetic energy. And we have this basic principle that I don't think I want to say much more about potential energy, because what I'm about to write down requires more than 2 minutes of explanation. 2 minutes is all we got left. Basically, what happens is the forces that act on a system can be split into conservative forces and non-conservative forces. So when you say the work done by the net force, it becomes the work done by conservative forces, which is the negative change in potential energy, and the work done by non-conservative forces. Okay, so you got the change in kinetic energy is equal to the negative change in potential energy plus the work done by non-conservative forces. Okay, and that takes a little digesting, more than 2 minutes worth. So that's what I was going to write down, but there's no point. That'll give you enough idea of potential energy to get a start on the assignment, along with what you have in the text and along with the example that we worked out in a good bit of detail. I mean, you're going to see examples in the text that you should be able to understand in terms of what we've talked about here. Does that make sense? Okay, and a lot of the examples are much simpler than the system we talked about. So build things up from simple systems to more complex systems.